Good morning, ladies and gentlemen. Welcome to the second morning session on Friday in MCC3. And I'd like to introduce to you Gregory Banks. Greg has been working as a Unix and Linux software developer in Melbourne for nearly 20 years, including several years as a Linux kernel developer working on NFS for Silicon Graphics. He now works for Opera Software Australia, previously Fastmail, where his duties comprise dragging the Cirrus IMAP server into the 21st century. Over to you.
Thanks a lot. Hi, I'm Greg. Only my parents and their government call me Gregory. And before anybody asks, no, my caps lock key is not dead. So I'm going to talk to you about Novaprova. And it's a new generation unit test framework for C programs. And incidentally, the title of this talk was something a lot zanier originally. I want to thank the conference organisers for their clever editorial input. So here's an overview. Why did I write Novaprova? Design philosophy and features, about 2 hours worth of talk about tutorial and how it works and stuff like that, which I'm going to be skipping through. So by the way, if anybody has any questions or wants me to focus on anything, just ask as soon as you can, because I'll need some guidance to work my way through the far too much material that I usually do. And then I can talk about some stuff at the end. So why did I write Novaprova? Fundamentally, I had an itch that I needed to scratch. It's a lot deeper than that, of course. So my day job is working on the Cirrus IMAP server. And it's written in C. Until recently, some of that was really, really old C. It is large, it is old, it is complex, and it had exactly 0 buildable tests when I first started my first day. And I asked, where's the test suite? And they said, what? So here's a little historical graph. This is a very rough measure of complexity. It's basically what I've done is I went through the Git repo and found changed lines. So it's counting every changed line twice. It's like pluses, minuses on your Git diff. Versus time. So the repo starts in July 93, and this is up to about a week ago. You can see over here, this is where I started working on the project, and that's where the tests starting existing. This is the non-test code in red. Down here we have this tiny little 2 flavors of test code. Incidentally, this huge jump in complexity is 2.3.16. That's what RHEL 6 ships today. Please don't use 2.3.16, we don't even know how to support it anymore. Anyway, this is not completely atypical of old C projects. So I started adding tests. I added system tests, I added unit tests, and I was using for my unit tests the C unit library because it's out there, it's available. I could just actually download it. It was actually a package on Debian. And it supports C, and it only supports C. This was actually an advantage for me because Cirrus, being very, very old, has things like variables called new and a struct called namespace. I wasn't going to try and deal with that, so I needed something that could compile with a C compiler and actually run with a C compiler only. And the first few tests are easy. It was like, it's great. It's like, hey, I've written a test. I feel good. And then they just got harder and harder and harder and harder and harder. Have I done well enough in testing? Is it tested enough? Well, this is a very, very difficult question. So I went out and did a little bit of research. I spent half an hour on Stack Exchange. And there's this code to test ratio metric, which I think is a completely meaningless measure of anything. But it is at least very, very easy to measure. WC minus L, very easy. So there are some people out there, including some really famous people, who have an idea that of what's too much of a ratio, too little of a ratio. So a 1:2 ratio in this thing means you've got twice as much test code in terms of lines as you do actual real code. That sounds like it's too much. And this is a guy talking about Ruby code, where if you believe all the stuff that people say about Ruby, you need fewer tests than C. 1:0 is too little. So let's look at some actual live projects. So over here we have the SQLite people who claim on their website to have 1,194 times as much test code as actual real source code. Wow. Well, yeah, yes, they are amazing. I bow to them. I wish they had a hobby sometimes, but you know, they need some time off. Anyway, so this is Valgrind. It's actually pretty close to the nominal sweet spot. This is Zapier, which is a C++ search library that I've been dealing with recently that I happen to have a repo lying around on my disk. It's not so well tested. And here's Thesaurus, the thing that actually stores emails, that actually runs our entire business. That's like, after 2 years of my work, is now up to 13.5%. So the conclusion from that is that there is lots of C code out there that people actually use using that matters, is economically important, that is undertested. And Cyrus is a wonderful example. It's very undertested. And why? Well, I used to have about 20 slides, and this is my first draft explaining all the connections about why, and why C is a poor language for testability, but fundamentally it comes down to it's too hard to write tests. Because there's a lot of things you want to do when you're writing tests that are very hard to do in a completely static language like C. So what we need is a better C unit, and that's what I set out to write for myself. And, oh, the button does work. So here's the design philosophy. I want to fully support C, and that's for my own personal use. I need to be able to build a test that runs completely with a C compiler and doesn't rely on interesting C++ features. So a lot of the existing C++ friendly unit test frameworks like CPP unit rely on things like being able to have macros that define little objects whose constructors get automatically called before main, and that's how they do test discovery. I can't have any of that. I want to choose power over portability because, you know, I'm a free software developer and I think portability is excellent, but on the other hand, it's important to be able to test the code at all properly on at least one platform. And so the C unit library that I was replacing had exactly the opposite philosophy. This was my main difference between them. They failed to do a lot of useful things simply because of portability, and they wanted to include Windows. So I prioritize your convenience in using the program over my laziness in writing the library. So basically, if I can do more work to make the job of testing easier, I want to do that. And I choose correct over fast, because it is very annoying to have slow tests. But today we have all kinds of fascinating continuous integration, gated trunks, stuff like that. People have ways of dealing with testing that are slow. Remotely debugging on someone else's site after you've shipped is far more annoying than waiting for a slow test. So I, again, am more interested in correct. And finally, well, choose the best practice as the default. I've been a little bit inconsistent with this, but the idea is that you shouldn't have to have somebody read a manual to work out what to do, how to do the right thing. The right thing should happen automatically. And finally, have the courage to do things that I've been told are impossible. So here's what Nova Prova does. Its features are, writing tests are easy. Building your test programs are easy. Tests are powerful. Test running is reliable, for several values of what reliable means. And integrating with other tools is easy. So writing tests are easy. So a test function, it's just a function. It takes no arguments, it returns no value. If it returns at all, it succeeded. All failure modes are failures to return. That's because in C, a lot of your failure modes turn out to be failures to return, like segv. So you actually need to be able to deal with that anyway, so why return a value? And you use if you've used C unit or any other X unit like thing, there is a whole bunch of assertion macros, which are, you know, check that these two things are equal kind of things, which should be very, very, very familiar syntax. All of them, unlike CUnit, are what CUnit calls the fatal semantics. In other words, the first assertion that fails the test. There is no keeping going, because mostly all the things that come after it are spurious failures anyway. And that really simplifies a lot of the logic. It actually simplifies tests. And I've written a lot of tests using CUnit, and you do things like have a fatal check to see if this pointer is null before you reference the pointer, because otherwise, it doesn't matter. It's pointless. You should just fail as soon as you fail. So here's an actual test. There are some examples that are going to be up on the website later. This is taken from them. You start off with including the header file. You include the header file for your own code under test. It's a function. Notice it's static. And it's called test underscore something. And it runs, this is a very buggy version of A2I that I wrote for the purposes of the test. And you run an insert macro, and it checks that it returned what you thought it did. And if you return, it succeeds. Otherwise, this thing, if it fails, pops out. Writing the main routine is easy. You don't need to muck about registering test functions. This is something you have to do in CUnit. You have to set up a structure with a map of a string to a function pointer, and blah, 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 blah. It gets difficult. Sometimes you need to basically arrange for test functions to be external. Then you've got to figure out how to name them. You can't name two things in two different suites the same way. It's blah, blah. So what I do is fully automatic test discovery at runtime using reflection. And yes, that's impossible. So this is your main routine. You include the header file. It's a main routine. There's this runner object. You create one. You run the tests. And you destroy the object, and then you exit using the exit code that you were given, which basically says a test failed or not. There are some more complex versions of this later, but that's fundamentally what we do. Notice, this is fully functional. You don't need at any point to register any tests. So, I've been talking to a few people at the conference, and when people hear that I'm doing a reflection, they're kind of interested in that, so I'm going to talk about that a little bit. So, reflection, for those who don't know it, is when a program detects facts about itself or other bits of the stuff executing in the same context. So in this case, we're talking about a library that knows about the names of test routines and knows how to find function pointers to them. All modern, where C isn't modern, languages do this. Because it's a really good thing. It has a limited use in each language, but when you've got it, you can do things like write test frameworks in a very, very sensible way. Now, C can't do reflection because there is no standard API, and the compiler doesn't write the info into the object files. But that's what people say. But in fact, it's not true, because the compiler will, if you give it -G, write a huge amount of stuff which is effectively reflection driving information into your object files, and when you link, the linker already knows how to aggregate those two in a way that it can be used later. Now, yes, that's not standard. Well, actually, it kind of almost is, because there's Dwarf, and almost every compiler on almost every major platform today, and no, I'm not including Windows, supports Dwarf. It is, and Dwarf is actually a standard. There is a standards organisation, such as it is. It's not much of a standards organisation. It has only one standard. But you can go there. You can download the PDFs, and the PDFs are they're pretty good. They're pretty readable. I like them. So it's used with ELF on Linux and Solaris. It's used with the Mach objects on MacOS, and compilers generate it. And it's a whole lot easier for me, as a developer of a library, to use information that the compiler already builds into my objects than for me to go and, like, I don't know, patch GCC to do something. I did that once. It took me 6 months to get permission from my employer. And by that time, the patch didn't apply. So I gave up. I'm not doing that. And if anyone's actually hacked on GCC, it's really gnarly inside, really, really gnarly. So it does it, it works. Anyway, so there's this argument that people say, it's only for the debugger, it's a debug format. Yes, that's what the D in Dwarf stands for. Sure, but so what? It's a general purpose description of everything that the compiler knows about the code that it wrote in the object file. Right? Sure, it was designed for debuggers. But there's lots of stuff in there that debuggers don't use. There's lots of stuff in there that is quite more flexible than that. So I think Dwarf is great. I think Dwarf is an excellent candidate. The only downside that I can see to Dwarf, apart from the fact that it ends up duplicating multiple... Andrew?
Could you just hang on a second? Get this recorded? If you repeated it.
Sure.
So why do this rather than just run a simple, like our Sambas McProto, which gets prototype headers? Why not, look for all your headers and just shove them in an auto-generated table and you're done?
Excellent question. And this is precisely what Cyrus does today. That's how all those unit tests that Cyrus has done. I wrote a Perl script that basically tools over all the test code and generates the data structures that CUnit needs. Two things. First of all, doing that in Automake turns out to be really, really hard. I ended up having to rename my .c files to .testc in order to convince Automake to actually compile them through this other wrapping layer to actually make things work. It was awful. Secondly, I basically wanted the absolute minimum build time impact on this thing, right? Because build time stuff is a pain. It's out of my control as a library writer, right? I wanted to shift the difficulty from the person writing the tests to the person writing the test framework. That was part of my design principles. Okay, which in this case it gave me a whole lot of difficulty, but it's for the test writer, it's enormously easier. Okay. So I created a reflection API. It's not entirely complete, but it does enough stuff for the purposes of Nova Prova. And it gives you a very high-level API. So it has an object that relates to a function, and you can do things like find the name of the function, find the fully qualified name of the function, find the enclosing class or struct or namespace or union all the way out, find its members, blah, 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 all that stuff. And it reads the dwarf info of the executable that it executes in. So there's a fairly simple procedure if you actually understand all this horrible stuff that took me weeks to work out. So you read proc self-exe, that finds the actual path name of the executable that you find without having to look at argv or even trust it. You then call this magical thing that is actually in libc but pretends to be part of the runtime linker, and it walks the runtime linker's map of objects, so you can find out all the actual objects that are shared objects and what have you that are linked in. You can basically compare that path name to that path name. That lets you tell where you're loaded. Then you can use libbfd to find the elf sections of this thing and then feed it the VMA addresses that you got from this. Did I say I had lots of complexity that I took upon myself? Yeah, you map that, you map the debug sections, and then you do the interesting bit, which is you lazily decode all that info. So I have a little object that basically walks over the dwarf attributes and the debug info section. And you ask it for a function and it goes walk, walk, walk. Oh, that's the function that, yeah. So yeah, that was quite a fair bit of complexity. But I had the courage to do impossible things. Runtime test discovery. Once you have reflection, this is easy. You just find all the functions, you match the names against this regex, and you pull out the bit that matches, which is the bit after test underscore, and that's the name of the test. We do some extra stuff that I'll go over later. And that's just easy. That just happens in the first few milliseconds after you start the library. So build integration. Build integration is really easy because it's just a library. And it uses C++ internally. The whole thing is actually written internally in C++, but there's a complete C API. You don't even need to link or compile any part of this thing with this C++ compiler. It's very easy to drop into your project. If anybody has any difficulty, tell me, I will fix that problem. It's designed to be as easy as possible to use. So I build you a .pc file, install it in the right place so that you can do this thing in your autoconf. The only downer is you need to build your tests with -g. I believe, and I haven't fully tested it, that you do not need to build the actual code under test with -g. Because it needs only to find the test functions, not the actual other code. Although if you're doing mocking, that's we'll get to that. So here's an actual makefile from an example. There isn't much. Package config tells you the C flags and the libs. You feed that into C flags, -g. This is your check. You build the test runner, you run the test runner. Not much to it. Find the test source. This is a very bog standard link line. Running the test is reliable. So we run the test under Valgrind. You may have noticed back in this makefile, there's no Valgrind here. So what happens is the test runner program Valgrinds itself. And it does that in a library. So what happens is, I'll go through that in a little bit detail. So we run ourselves under Valgrind because we want to achieve the best possible detection of errors all the time. So there is actually a way to turn it off, but I'm not even going to tell you what it is. We have strong test isolation, and we get the best possible test isolation is we use a separate Unix process for each individual test function. So we fork a process per test. This allows for a lot of neat things. For example, we can do timeouts properly, we can run things in parallel properly, and we isolate a lot of test failures. A lot of test failures. So here's the process architecture. You have test runner, it Valgrinds itself, and then it forks as many tests as you're running in parallel into children, and these are also already Valgrinded because that basically just got inherited across the fork. It turns out forking a Valgrinded process is a lot faster than Valgrinding a fork process. And here's what happens when you run. Your test runner runs, says hello, running mytest.simple, nothing happened, pass, one run, one fail. That's all you do, you just run the test runner. So how do we Valgrind ourselves? Well, it's easy. You build a command line. The command line has user bin Valgrind at the front. Then it has your executable name, which we found before using proc_self-exe. And then it has the original arguments. Oh, isn't that interesting? We'll get to the original arguments. So there's a couple of downsides to that. The first downside is main, the bits of main before you do this is run twice. I haven't figured out a good way to fix this. But what I've done is I've moved enough stuff into the library that your main should not have anything with interesting side effects. So I think I'm not worried about this. There is a major downside. If you're not careful, it'll just keep doing that and re-Valgrinding itself. So what we need to do is make sure we're not running on Valgrind when we do this. And there is an API that Valgrind gives you that has this predicate running on Valgrind, which tells you whether you're running on Valgrind. So you just check that. That's very easy. Yeah, getting argv is interesting because it's a library and it doesn't have access to main, and I don't want to trust main to actually correctly pass things down, and because a whole bunch of stuff like that, because main could be doing any kinds of get-op processing and you never know how it does it. It could be doing it destructively. I want to get the original argv, or as close to the original argv as I can, in the library without passing them down from main. So I dug around and I found this thing which is undocumented, undeclared, defined in the runtime linker. Yes, it's a hack. Nevertheless, it is set to main's real argv before main runs and remains there. Parallel running. Now, because we fork a separate process for each thing and we basically wait for test completion by waiting for the process to finish, it's easy to run more of them. There's this API that you can set on the runner object that'll tell you that. That's very easy. So here's a slightly enhanced main. We do a bit of get-opt, we check the concurrency, we call npset concurrency, and that number there makes it happen. So here's parallel 4 tests running on my one CPU thing, but fortunately they're all doing sleep, so it doesn't really hurt things. So it starts off test 0, 1, 2, 3. This is the test, this thing at the start of the test saying, then they all slept for a while, and then they all finished, and then it said pass them. And note they're in a different order. This is basically just what comes out of wait, weeping, children dying in various order, and the past. It's very easy. Using GDB, sometimes you need to debug your tests. So you have a test timeout, and this is the one thing that I had to add a test timeout feature to Cyrus to work with CUnit. And I had to add an option to not have a test timeout, because when you run it in GDB, the last thing you want is you're halfway through debugging and suddenly you get a SIG alarm and everything goes to pot. So you don't want that. So this thing automatically disables test timeouts when you're running on a GDB. Also, GDB and Valgrind don't play together well. So it needs to not do the whole Val grinding yourself dance when you're running on a GDB. So basically what we do is we need to work out that we're running on a GDB. And well, we did. There's some awful stuff we need to do here that I can probably fix later. But basically, you run the test runner, you put a breakpoint on the actual function, you run it, it says, oh look, I'm being debugged. La 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 la, disabling test timeouts, and then it breaks in breakpoint. So it's easy. How do we detect GDB? So basically we detect that we ptrace. So there is this file, you can look in basically proc self status and it will tell you tracerpid is the process ID that is ptracing it. But other things also ptrace you, like strace. And you need not to do these things with strace, because strace isn't going to play nice and set breakpoints with you. So we actually reach over, find out what the program that is stracing you is, using several other proc lookups again, and we figure out whether it's GDB. And if so, we say yes, it's GDB. Oh, by the way, proc-pid-exe, very convenient, not actually readable if your debugger is running as a different user to you. So I had to do that the hard way too. Using Jenkins. I love Jenkins. Anybody who's been here has heard people talking about Jenkins. Jenkins. I think it's the best thing since sliced bread. In fact, I think it's better than sliced bread. This is an actual example from the Cyrus Jenkins server, public instance that you can see. And it's the historical set of these are test failures, these are test passes. And you can see this is where I added the system tests, and before there was just the unit tests. And this was me writing the unit tests. And as you can see, it's been done stable for a while. There's a bug where it fails to run a whole bunch of tests. And so Jenkins is great. Jenkins will do all these neat things with it for you and let you explore test failures and such like, but you need to feed it with JUnit XML format. So we build that, and there's an NP set output format. And it's very easy to call. You call it that, the string is JUnit. Here's an example, here's how you write it, test runner minus format, JUnit, la 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 la. You don't get any of your output, instead you get this directory with this file, and this file is this XML cruft, which as far as I can tell is exactly JUnit. It's a bit hard to tell what JUnit XML format means because there's no actual DTD for it. I found somebody had reverse constructed a DTD and it now satisfies that, but I'm not 100% sure. As far as I can tell, it works. If it doesn't work, tell me. Also, I haven't done these yet, so just pretend that doesn't happen. Fixtures. Okay, fixtures. Fixtures are, if you know anything about XUnit lingo and testing, fixtures is where you have common code that you use to set up some kind of shared resource that multiple tests use. So what we have in this case is you have a setup and a teardown function. And we very simply call these setup and teardown. And they're discovered at runtime using a collection. So it has to be the right signature. It fails if it's not the right signature. Returns an int, takes 0. It really shouldn't return an int, that's beside the point. So in this case, we just print a message saying obvious stuff. And here's this running. So we're running my test. This is, there are 2 tests in this suite. First one says we're setting up fixtures, running the test, finish running the test, tearing down the fixtures, and then do that again. So it's just common code that you can use to set up something that's needed by all those. And again, we make it as easy as possible here. You just create a function with that name. Now,
does that mean that when you're running the fixtures, Does that mean that when you're running with fixtures, the testing doesn't occur in parallel?
No, not at all. It's just a function that gets called many times, potentially at the same time in same. So you can. It's completely orthogonal to running in parallel. Okay. So what it means is every time you have a test function that gets run, it actually looks up all the ancestors of that test function. They're organised in a tree. And it says, well, this is the set of setups that I need to run, and it runs all those. And it does all of that in the child. So back here in this example, oops, doodle, thank you. The fork happens here. Sorry, here. This is emitted by the child. All these things down here are emitted by a child. This one here is emitted by the parent when the child has sent a packet back up a pipe saying, I've passed.
Do you handle test dependencies at all?
No. I do not handle test dependencies, not because I'm lazy, but because I actually think they're a very bad idea.
Can you elaborate on that then?
You bet.
Hang on, here's Cyclops.
So what is a test? I personally believe in the Gamma-Beck definition of a test, of being an independent unit, an independent piece of stuff that doesn't rely on other things. I believe in test isolation, and I do not believe in test dependencies. I want each bit of code, each test, if it needs to test interactions between bits of software, it should set those interactions up. I don't want to have to ever have to run one test before another test can succeed. I think it's a silly idea. If you're doing that, you've got two halves of one test. If you have such a thing, then I have a method for you to do that. You put the first half in the setup, and it's not part of the test anymore. Incidentally, if the setup fails, the setup routine can actually fail. It can throw assertions and can return non-zero. If any of those things happens, then it fails the subsequent test. So there is no need whatsoever for test dependencies. Stuart.
Very loudly and still in the microphone.
This is actually needed for the recording for people that listen afterwards.
Or for volunteer exercise. But I was just wondering with the setup, so we have some setup stuff that can be fairly expensive.
Yes.
And is it more of like to group that together and then sort of fork off many other ones? Is that a thing on the radar, or does it do that? As well as other setup that, like allocates TCP sockets and files on disk that do actually have to be done each time.
I understand that guys like MySQL, and I've had the same discussion with Andrew Samba, there are things that where you have expensive resources to set up. I haven't written for that because Cyrus, so you saw all those several hundred tests that Cyrus runs. In my system tests, Cyrus will basically start in about 30 or 40 milliseconds, right? And it takes you another 10 milliseconds to set up enough directories and files and SASL rubbish to actually start a trivial instance. So what I do is I will start 1 or 2 or 3 or 4, depending upon the system configuration, complete Cyrus instances in basically 0 time flat. And I set up, yes, it is so good. And so the system tests have total isolation. I went to the test repository talk, and there's all this brilliant stuff about working out when they're interdependent tests by figuring out, okay, this will run in the same worker, therefore there may have been state left over from the first one. So my philosophy is make that not happen. Don't try to figure it out afterwards. Chop off the state entirely. Now, I haven't done a complete job of that, but I've done a start, and I've got the architecture there. So you can basically work out after a test's finished that it has not polluted any part of the environment. My belief here is that isolation is better than anything else. This is why I run Valgrind as well, to find things that would not pop up except as later failures. Okay. What was I? Now, tests are a tree. Now, C-unit stuff, at least all the ones I've seen, all the X-unit things, they organise tests in a very, very simple two-level hierarchy. It feels like VMS. You have a test, which is the smallest runnable element, and you have a suite, which is just a group of tests, and that isn't good enough for me. And software isn't like that anymore. Nobody builds modules like that anymore. And so what I do is I have an arbitrary depth tree of things that I call test nodes, which are either tests or suites. And in fact, they can be both. You can in fact have a test node that has both a runnable test function and children. So this is more like the IMAP tree model than anything else. And it has fixtures. So you can have 4 or 5 or 7 levels deep, just a moment, of test nodes, and you can stick like a setup at the top and have that run before every single one of all your tests, or halfway up. So you can basically stack your setups, right? And there's several other resources like mocks and so forth are attached to these things. And this is actually an incredibly flexible containment mechanism and organisation mechanism. Now, the test is built automatically at runtime. Okay, sorry, Thomas?
Quick question. You're dynamically discovering all the tests that you're running with that multi-step evil process.
Yes.
Have you thought of a mechanism to alert you when it suddenly stops finding a test in case it drops out? I mean, you'll see the sort of the Jenkins graph drop, but anything scary or automatic?
No, it doesn't keep any state between test runs. And I'm glad I didn't do that because test repository exists and it seems to do all that very brilliantly. So I highly recommend you look up Robert Collins' test repository. That's my first shiny thing I'm going to play with when I get home. Okay, so it's fairly straightforward. We find the leaf nodes, or we construct full path names from the leaf nodes using C-source file names. And I'll give you a nice example of that. So here is some fairly silly tests. This one's called Torpedoes. It's in a .c file called Star Trek TNG Federation Enterprise.c. And what we do is we get this is the name of the directory above that. This is the name of the example directory in this case. And then we get .startrek.tng.federation.enterprise. So this is the directories, that's the .c file name, this is the name of the function with test underscore removed from it. So it's a very, very simple mapping. Okay. Now function mocking, I want to talk about this in my last few remaining minutes. Because this is also really cool. This is cooler than reflection. So mocking a function in XUnit speak is basically arranging for a particular function in the code under test or in libc or other places like that to be called to, when it's called, to go off and call some other function that you control in your test, which can then pretend to simulate that behaviour or can do some extra checks on it or some other things. It's an amazingly powerful mechanism. It's almost impossible to do in C, almost. So there are several libraries that will, test unit frameworks that will do mocking at build time. Big problem with this. It's also easy to set your own up because, you know, normal shared library semantics, you can do shared library shims, you can do all kinds of stuff, preload shims. The big problem with all of those is that those things are done statically at runtime. And so you can't say, I want to run my foo function 14 times, insert a mock function, check something, remove the mock function, go off and run it a few more times. You can't do that. You have to build that state, if you want it, into the mock function. Which means if you want to mock a function and then test it 14 times in 30 tests, you've got to have all of your, you know, the cross product of all those tests and all the state they have in your mock function. You can't have 14 mock functions each doing a tiny thing. It's really awful. So what I do is I do it dynamically. I insert at runtime a breakpoint into the code. Okay, so there's an example here. I have my A2I, an incredibly buggy implementation of A2I, which calls my charter int, which is here. And what I want to do is, in my test, I want to say this thing gets called instead of the real my charter int. And it's going to print a message to do it, and then actually in this case simulate the exact behaviour of my charter int. And this is what happens when you run. So you're running the test, the mocked function got called, the mock function got called, and then we passed. And I'll point you out that this code knows nothing, this code the code under test knows nothing about the mock version of this function at compile time or at runtime until here. It's not a function pointer. This is a normal function call of a function in the same file. And how do we do that? We use this mechanism called intercepts. It's actually a lot more powerful than mocking. You can do other things. But what happens is we use a breakpoint-like mechanism. It's less general than real breakpoints. It only works at the start of a function. And there's a few other limitations. And the way the first thing we do is we basically insert a breakpoint. So here's our process, here's the text segment, there's our target function. And the very first time that we're intercepting the function, because you can have multiple of these intercepts chained together and it calls them all on the same function. It makes that page writable. Fortunately, Linux lets you always do this, make a text page writable, even on your own process. And then we basically have some ref counting for that. We overwrite the first byte of that function with the Intel halt instruction. And then what happens is when you actually run the function, CPU says, oh, trap. We get segv delivered to the process. Now the signal handler is a really evil piece of stuff in a very, very strange state, and we want to get out of there really quickly. So we do a lot of stuff, end up popping out of the signal handler into another function, which is the trampoline. That trampoline sets up a fake stack frame, calls the intercepts before function, which allows the intercepts before function to futz with the arguments, change the arguments as we go. Then it calls the target function with that fake frame, or it may call another function entirely. That's how the mocks work. Actually, we call it a redirect. So it basically goes over here. Oh, I'm in the before function. No, I actually want to go over there. And then finally, it cleans up all the mess that's left on the stack and then returns back to the target's caller. That is, how should I put this? System dependent. And it's complicated. So it turns out it's actually much harder to do on 64-bit because I relied on this trick that the first instruction of almost every single function in 32-bit is push L EBP, and I don't remove that one. That's a 1-byte instruction rather conveniently. So you have complete instruction stream after you have pushed in the first overwritten the first byte. So I simulate that instruction in the caller. That doesn't work on 64-bit because it's a different ABI. The procedure linkage table makes life difficult. Floating point state makes life difficult. And it turns out that GDB and Valgrind, there are actually 2 ways I could have done this with different instructions and different signals. And you can't, there's no way that works on both. So I have to basically detect if I'm running on Valgrind and do a different thing there than if I might be running under GDB later. Because you can always GDB attach to a process that's not running Valgrind. And then I get about a million other things to do. I'll zoom through this and show you the further work, and then we'll have any last questions. Last questions? Yo.
I was wondering if your mock functions have the sort of usual reporting you have in other sort of mocks things where you say, yes, I was actually called, and yes, the first variable was,
yes,
a number.
Yes, you can do that. You get your mock function gets a copy of all the arguments that got passed to the original function. It's the return value of the mock function is returned to the caller as if the original function had returned it. So you can completely fake out its side effects and its actual visible behaviour, and you can do asserts in there, and you can set other state. If you have like a variable somewhere that says whether this thing passed, you can then check in the main routine. So you have complete freedom.
The mock function itself checks what it got called. It's not some of the other ones. You can basically say run the mock function, and then afterwards in the test part say
you can do it either way.
With
you have the flexibility to do it either way.
Good, thank you.
As you can see, there's a lot of stuff left to do.
Questions, yes?
So I saw when you were talking about the mocking, I think there was a reference that it only worked in C++. Was that?
Oh,
Is that all-
no. It actually works on any function, so I can actually mock out libc functions. Basically, if you have something that is actually a function and not some weird thing that happens to have an address, so it does deal with the stack properly, and it actually obeys the ABI. It can be a C function, it can be a C++ function, as long as you can work out what arguments to pass it and call it from your code, you can intercept it. It works on an instruction basis. What's the license? The license? When I open sourced it, they made me give it the Apache license. I was going to BSD license, but whatever, I didn't care. It's free and open source. Otherwise, I wouldn't be here talking about it, right? Anyone else? Yeah, please.
If I cross-compile, can I have the mocking not get in the way?
If you cross-compile,
Yes.
what?
I mean, can I use it in a cross-compiled system and have it work, but not mocking?
If you cross-compiled to... Okay, so you're basically saying if I strip out all my clever features and you run it on a platform I haven't ported it to, will it work? Yes. I'd have to do a little bit of futzing with the build system to make it not fail when it doesn't recognise the arch. And of course, the Valgrind thing probably won't work if you're you're probably thinking of ARM, right? Yeah. More or less everything else should work. If you're running Linux on ARM, then the other bits should work. It'd be an entertaining project. I'd love to try it, but don't have an ARM box at home to play with. So, well, I mean, one that isn't my iPhone.
Yeah, as Greg says, that's all, folks. So thank you very much indeed for the presentation. And on behalf of the LCA 2013 committee, a blanket to keep you warm.
Thank you.
I guess you can come down and ask questions if you wish, no problems.